Good day to all the participants of workshop, and I want to deliver the topic use of nonlinear models to estimate the spatial temporal distribution of organochlorine pesticides. Did you know that in Ukraine the range of pesticide is about 268 names and their tonnage reached 36,000 tons, while the need is 4,000. A number of assessment to pesticide by the criteria of toxicity, persistence in the environment, migration, bioconcentration, and actual contamination of objects refers to the 1-2 class of hazard. The leading component of methods to control the limit the harmful effects of persistent organic pollutions on the environment is comprehensive monitoring of the distribution of their residual concentration in space and the evolution of this distribution over time. However, the experimental results of such monitoring accumulated to data are fragmentary, non-systematic, and highly discrete. This nature of the accumulated data doesn't allow us to obtain reliable estimates of pollution level in the intervals between the control points of persistent organic pollutions concentration. Thus, the need to us adequate and reliable predictive model built on statistically small samples of monitoring data is evident and urgent. To address this problem, this study compares the performance of 3 machine learning algorithms for regression problems called CatBoost, LightGBM regression, and XGBoost algorithm for the spatial and temporal distributions of organochlorine pesticides. The aim of the work is to compare and evaluate different regression models based on model evaluation metrics. So, if we talk about algorithm extreme gradient boosting, we can resume that an ensemble algorithm for machine learning based on decision trees using gradient boosting technicals. Boosting is an ensemble technique in which new models are added in order to correct errors made by existing models. Models are added sequentially until the next improvement is reached. Many practical applications of gradient boosting tend to minimize the objective function. At each iteration, we set the base learning object to the negative gradient of the lost function, multiply our prediction by the constant, and add it to the value to the previous iteration. Fitting a base learner to a negative gradient at each iteration essentially performs gradient descent of the lost function. XGBoost algorithm works by sequentially training a set of weak models called by learners. Each base learner aims to minimize the error of previous model. In this case, learners are added to the ensemble with weights corresponding to their effectiveness. Here on the slide, on the left corner, you can see the pseudocode of XGBoost algorithm. If we talk about CatBoost algorithm, the main idea for processing non-categorical features in regression problems is to use gradient boosting and apply regularization to obtain more accurate and generalizing models. Although the cut-boost algorithm is designed specifically for working with categorical features, it is also effective when using non-categorical features. Here we can see a few key features for this algorithm. What is this? Missing value handling, regularization, optimization of deprivation function, automatic selection of optimal hyperparameters. The main idea of the cut-boost algorithm is processing non-categorical features in the regression problems to apply regularization, optimization of deprivation function, and automatic selection of optimal hyperparameters to create optimal, accurate, and generalizing models. Cut-boost algorithm have such an advantages: reliability, automatic feature processing, simplicity in the table, and performance. On the left corner you can see the pseudocode of cut-boost algorithm. And the last, Lytvynenko algorithm. The main idea is to develop efficient and fast gradient boosting for solving regression problems. It is an optimized version of gradient boosting and has a number of key features. Build and 3 vertically, leaf-wise 3 growth, histogram-based optimization, accounting for categorical features, and parallel processing support. The Lytvynenko algorithm is based on the idea of using efficient optimization and parallel processing to achieve high performance and accuracy when solving regression problems. It is widely used in various fields where fast and accurate prediction of numerical values is required. Benefits of Lytvynenko is it can work with large amounts of data with significantly reduced training time. It has a possibility of parallel learning. It uses much less memory, high learning rate and efficiency due to histogram algorithms, high accuracy of boosting results. Since Lytvynenko builds quite tiny trees following the split by leaf approach rather than by levels. On the left side on the slide you can see the pseudocode of Lytvynenko algorithm. On this slide you can see there are 3 tables. Each of table contains of metrics of each algorithm, and we have the experimental results. And I should say that as a result of experiment have shown that XGBoost algorithm is the efficient algorithm with good performance. It offers a wide range of features, supports regularization, and has flexible parameters for model optimization. The Lytvynenko algorithm demonstrates high efficiency, fast training time, but low memory usage. cut-boost performs well and provides built-in support for categorical feature Viva. In our research, based on the accuracy results presents in tables 1, 2, and 3, we would prefer the XGBoost algorithm for solving our regression task. The comparison of accuracy between Lytvynenko and XGBoost in solving regression problems may depend on the specific dataset and model parameters. Both algorithms generally exhibit high accuracy in regression tasks, but the results can vary depending on the data characteristics. The main objective of this paper was to find and evaluate adequate and reliable methods for constructing predictive models built on statistically small samples of monitoring data. Therefore, our task was to compare and evaluate different regression models based on model evaluation indicates. Experimental data describing the spatial and temporal distributions on concentrations of different pesticides across the provinces were used as a data set. We were able to explore different regression algorithms and apply these algorithms to the data set. The study was conducted in a R environment. In a contrast, the reference vector regressions showed the lowest results. From the study in our dataset, XGBoost regressions showed the best results for all the indicators. So, I'm finished. Thank you for your attention and good luck!